Hello, welcome to our 13th lecture, where we'll be discussing the definition of the derivative. Now, the derivative is something that we'll be in for quite a while, but it'll look a little different in the future. Today, like the title says, we're getting into the very definition of it, which has to do with limits. But we will take that limit focus off of things in the future. So you might be excited about that. We do have to start somewhere. All right, so this is a little bit of review. The instantaneous rate of change, the rate of change at a single point, a single instant, at x equals a of a function f of x. So this was a slope. It is the slope of the line which glances, just touches at one point. It just glances the function at x equals a. And the idea behind this is that it tells us how fast the function is increasing or decreasing. So a little picture. Let's say this is my function, my graph y equals f of x. Got my axes here. And let's say this is the x value a. So the instantaneous rate of change is this line which just glances the function at that point. It only touches the function there, at least locally speaking. And this we discovered by finding a limit. And here's the main version. There were two versions, but we use the h one. And the idea is that h is a very tiny x distance along the x-axis. And now this part is going to look like a slope because it is. A plus h. So that's just a tiny, that's a point that's just a tiny little distance away from A, which is on the graph. So this is like a tiny rise, difference in y, over a tiny run, the difference in x, a rise over run. And as h approaches 0, that gives you the slope of this blue line. So this line is called the tangent line. Because tangent means it touches right at that point, it glances the curve. So the slope of the tangent line is the instantaneous rate of change. tells you how quickly your function is rising or falling at that point. So, for example, you make a little graph like this. And let's say my x value A is here. And the tangent line is horizontal. I'm drawing a dash this time. It's not a big deal. So if the tangent line at this x value A is horizontal, then this means the instantaneous rate of change at this x value is 0, effectively no change. And the reason is that the slope is the same thing as the instantaneous rate of change. The slope of a horizontal line is 0. So that's pretty much review. I didn't give the name of the tangent line last time, but that's what we were doing. The derivative gives us a powerful tool which lets us find a lot of these instantaneous rate of changes. So we want a way to find the instantaneous rate of change, not just at a single x value, A, but any x value we want. So that's what will make this more powerful. And this is achieved by a new function called the derivative. So the derivative is essentially a formula that will let us find the instantaneous rate of change at any point. So once you find the derivative, that's taking a limit once, at least for now. Again, later we won't do limits, but for now we take a single limit, and then that gives us a formula which will allow us to plug in any x we like to get the instantaneous rate of change. So just take a limit once to get any instantaneous rate of change. Let's underline derivative. So now let's talk notation. It's written as a fraction, but it's technically not literally a fraction. This is an operator. So down here is the variable or the input of your function. So if we're doing a physics problem like with time, then it would be a d dt. That's how we say this, d dx. It's whatever your input variable is. So this is the derivative operator. Don't worry too much about that wording. It's just the idea is that this is the action of taking a derivative. Where it represents the process of taking the derivative. I'm going to abbreviate derivative as dir. So the way this works in practice is you have this operator applied to the function f. And so what this is saying is that we're taking the derivative of f. So you take the derivative of f, and then there are three ways to write the outcome, and we'll mainly focus on two. So here's the least important way. I wouldn't worry too much about it. You can write it as df dx. So for the operator, it just has a d in the quote-unquote numerator. But this is an actual function, the derivative, where you have df in the top. But we're not going to use that notation too much. Typically, we'll say dy dx, where y is the output variable. And another way is f prime of x. So these three things, it's just notation, which all means the same thing. It's the derivative. I think this exists in part because calculus was invented by two different people independently, Isaac Newton and Leibniz. So that's why we get this dual notation. But they're both useful at different times, so I think it's valuable to have both. So when you see these things, we're talking about the same exact thing. dy dx and f prime of x. They're both the derivative of f. So let's actually calculate a derivative. Square root function and it's only defined for positive real numbers and 0. So f prime of x, the derivative function, is the limit as h approaches 0. This is going to look just like an instantaneous rate of change, but we replace the specific x value a with just plain old x, a variable. So not a huge difference. Just we're using the variable x instead of a particular x value. I want to write that real quick. Oops. X value. So again, this is not a huge difference from what we were doing last time. It's just that once we get to the end of this, we'll have a formula which will let us find the instantaneous rate of change anywhere. All right, so f of x plus h. That means x plus h is getting plugged in place of x here in the function. So the square root of the whole x plus h minus the square root of x over h. I actually want to move this. Well, if you try to plug in 0 for h, that's going to be problematic, isn't it? Because this would turn into the square root of x. Square root of x minus itself is 0 over 0. So plugging in 0 for h doesn't work. So the trick is when you have square roots involved, you're probably going to want to multiply by the conjugate. Let me use my alternate color. So I want to multiply by the conjugate, which means we just change the minus to a plus. But to keep things equal, I have to do it to both the numerator and denominator. So this shakes things up a little bit, and hopefully when we're done, the limit will be more manageable. So, piece of advice, this is the sort of trick you want to do when you're stuck on a square root limit. Okay. So when we multiply the numerator by the conjugate, you FOIL, and I'm going to save a little time. It ends up being the square root of x plus h squared. So square root disappears. The outer and inner terms of the FOIL, they cancel out because you have the minus and the plus over here. And then it's a minus x when you square that square root of x. Now the denominator is going to be a little messy, but this is actually okay. So notice up top, we have a plus x and a minus x. Which leaves us with just an h in the numerator. Cancels with that h. So I'm doing two steps at once there. Here's what we're left with. Just a 1 left up top because the h canceled. Now it might look a tad messy, but notice that when you plug in 0 for h, this actually works out just fine. So now I stop writing limit because I'm plugging in the value 0 for h. Since this is plus, they're adding together, not canceling out. So you can simplify like this. So now this gives us an expression which allows us to calculate the instantaneous rate of change of the square root function at any x value we like. So let's practice that. few parts here. When x is 1, the power of the derivative means that I don't have to do the limit again. I have a formula now. So let's write it like this. F prime of 1, plugging 1 into the derivative function, one over 2 times the square root of 1, 1/2. If I want the instantaneous rate of change at x equals 9, okay, plug 9 into the derivative function. Okay, and we get 1/6. All right, what about when x is 0? That's in the domain of our function after all. Okay. Uh-oh. That's a problem, because this becomes 1 over 0. It's undefined. So it turns out there was a slight flaw in my derivative. It's undefined as 0, and you can tell when you really look at it. Right? If I plug in 0, that's a problem. Also, any negative number, but we're not focusing on that because that's not in our original domain anyway. So for x values, which are in the domain of our original function, there's only one which gives us a problem, 0. So f prime of 0 does not exist. Now this leads us into a discussion of what's called differentiability, meaning when are we able to take the derivative? We say the function is differentiable and I'll often abbreviate that as diffable, because differentiable is a big pain to write. So differentiable at a particular x value, a, if the derivative exists at that point. So your function is differentiable at a point if you can take the derivative there. That's what it means. And we say the function overall is differentiable if it's differentiable at every individual point. And I'll abbreviate that. And need to be a little specific, every point in its domain. So any point where the function itself exists. Right, so this is an interesting problem because there are a few different ways where you can fail to be differentiable. I'll show you that. So first we're going to focus on one-sided limits. Remember, the derivative is a limit, so that means in order for it to exist, it must agree on both sides, left and right. So that's the first thing to consider. And I'll just say a little thing here as appropriate with the domain. Don't worry too much about that. That's just getting into the weeds a bit. So we need both one-sided limits to exist and agree. That's when your overall limit exists. So this as appropriate with domain part. What I mean by that is if we look at the previous problem, notice we have a hard stop at 0. So that means that it doesn't even really make sense to talk about a left-sided limit when you're at 0 because there are no x values to the left. So in that case, we don't worry about the left side too much. So that's all I mean. All right, so the one-sided limits. That's just h approaching 0 from the right. And at the moment, we are talking about particular points. So I'm using A. Needs to agree with the left. So in order for your derivative to exist at A, these one-sided limits need to exist in the first place and then be equal, as I've written here. So we call this the right hand RH, the right hand derivative, and the left hand, derivative. And that's because we're approaching h from the right versus the left in these two examples. So let's see why this matters. We'll look at an example where this fails. A good one is the absolute value function. So quick sketch of the graph. Looks like a V. The idea of the absolute value function is you plug in a number and it will spit out the positive version of that number. So it's f of x. We write it like this, these bars around x. And in particular, this is a piecewise function. So when x itself is positive or 0, this just gives us back x. Hence over here we see the line y equals x. But if x is negative, then we take the negative of that negative to make it positive. So this is when x is less than 0, or x is negative. Hence, this left side looks like the line y equals negative x. So this little construction ensures that you're always getting the positive version of whatever you plug in. So most points are fine when it comes to differentiability. The problem is when x is 0. This little vertex here. So let's look at that. So I'm not calculating the entire derivative, but just the derivative evaluated at this one particular x value. Well, we'll actually see that it doesn't exist here. But we'll try to calculate it. All right, so notice I'm plugging in a particular x value here because we're just looking at x equals 0 minus f of 0 over h. Now, note here, we're going to use in particular this expression, and the reason why is because of h itself. H is approaching 0 from the right, which means that h is positive. That means this 0 plus h is positive. So note that 0 plus h, which is of course h, is greater than 0 because we have h approaching 0 from the right. So that has a big effect on this limit. We're plugging in a positive number, so we just use the identity function. Plugging in 0 plus h, we just get 0 plus h back because it's positive. And f of 0 is 0. Okay. So h over h, 1. So that's the right-hand limit, or the right-hand derivative, if you will. Notice that it's the slope of this line, and that's no accident. Because the tangent line is just the line itself, because it's already a line. So this is the slope of the tangent line on the right side. All right, let's look at the left. So similar construction, but h is approaching 0 from the left this time. Well, in that case, that means my h's are negative if we're on the left side of 0. So note that 0 plus h, which is h, is less than 0 since we're approaching 0 from the left side. This is important because it means when I plug in 0 plus h into f, that's a negative number. So we take the negative of that negative to make it positive. So, all right, this is technically I'm showing some extra work here. The negative of 0 plus h Well, this is just negative h over h. Negative 1. So notice that that makes sense with the graph, because we're looking at the left side approaching 0. And the tangent line will be the same as the line itself, has a slope of negative 1. So notice that these one-sided derivatives disagree with each other. We're coming at the point with two different slopes, as we see here. This means the derivative does not exist at this point. Or in other words, f of x is not differentiable at x equals 0, because we have that disagreement with the one-sided limits. So the way that you can tell on a graph, at least one of the main ways, is that we're never differentiable at corners or cusps. So corner, that's like what we had in the previous problem. We have this sharp change, which means the derivatives on each side are different. So there's no full derivative at this point. So sharp corners and cusps are pretty similar. It's just more like a curve. But similar thing, you're having a very sudden change in your slope at that point. So the derivative does not exist at that point. So, whoops, again, this is because right hand and left hand derivatives disagree. So there is no full derivative at those points. Now, here's another thing to look for, a little bit different. Also, you must be continuous. So when we talked about continuity of a function, we weren't wasting our time. Function must be continuous to be differentiable. All right, now the question is why? Why must we be continuous to be differentiable? Well, I'm not going to give an absolute proof, but a solid example. Let's use some different letters. We'll make a piecewise function. Looks like 2t at every point except when t is 1. And when t is 1, it's just at the value 1. Let's make a quick graph. So notice my input variable is t for this problem. So it's a t-axis. And we'll just use y for our output, but that could be different. All right, height 2. So it looks like the line 2t almost everywhere, but we're going to have a hole at that point. Notice this one, whoops, this one passes through the origin because it's just an mx form or mt form in this case. The y-intercept is 0. So a line with slope 2 that passes through the origin. But when t is 1, we're at height 1. So fill in the dot there. So this is a valid function. It passes the vertical line test. But as we've seen in the past, we're not continuous at this point. It's a sudden jump because the limit as t approaches 1 here, we're headed towards this y value of 2. So the limit is 2, but the actual function value does not agree with that. It's 1. So we don't have to walk through that all over again, but just say that we're discontinuous at t equals 1. And everywhere else is totally fine. It's just a regular polynomial 2t. And it turns out that you're also differentiable everywhere, except at this point. But I haven't shown yet, why do we fail to be differentiable at this point? Well, it's actually not the one-sided limits that are the problem this time. Something else. So let's attempt to calculate g prime of 1, the derivative at t equals 1. Right, so this is my particular t value. So this is a slight change in y over a slight change in x. Or t in this case. All right, plugging 1 plus h into the function. It's important to note that when we say h approaches 0, we're saying that we're getting very, very close to 0 without ever quite reaching it. It's like an asymptote, if you will. So if I'm plugging in values which are not quite reaching 1, because this is 1 plus h, and h is not quite 0, that means we use this formula, because the thing we're plugging in is not 1. So 2 times the whole input. So I'm using that 2t formula. And this is over h. Now what's g of 1? Well, for g of 1, we're literally plugging in 1 for t, so we have to use this. So we use the 1 instead of the 2t formula. Now this doesn't look too bad right now, but it will cause us a problem. Distribute the 2. And we can combine the like terms, the 2 and the minus 1. So let's write the 2h first. Excuse me, that's plus 1. There we go. Now, notice that we're not quite able to cancel h because we don't have an h in both terms. That plus 1, it's missing an h. So that's what causes this to be a problem. It can be helpful to separate out this fraction. You can do this. The sum of two fractions with the same denominator. Now this first part would be fine. The h's cancel, you just get 2. But I'm not able to cancel this 1 plus h over here. But we can actually finish the problem. It's only when you have a 0 over 0 where you can't tell what's going to happen. It's called an indeterminate form. The same is true of infinity over infinity, but I'm talking about 0 here. But this is actually 1 over 0, it's becoming. And we actually know what's happening there. I'm taking 1 and dividing by very, very small numbers. That means this part is approaching infinity. Could actually be plus or minus. And that difference would boil down to which direction we're approaching 0. But it's not a big deal for this problem. Because we have infinity involved, it means that this limit does not exist. So when you have this sudden jump, like we see in the graph here, we're discontinuous. If you try to work out the derivative at that point, you'll get infinity or minus infinity, which does not exist. So in conclusion, the function g of x is not differentiable. Oh, sorry, not x. It's t. Let's be consistent here. It's not differentiable at t equals 1. And the real reason is because we were discontinuous. But we worked it out with the limit. This is the true underlying reason. If we were continuous, I'll just end with this. If we were continuous at that point, then what would have happened differently is that this would have been a minus 2 instead of minus 1, right? Because we just forced g of 1 to be 1 when it kind of wants to be 2 if we plug in 1 there. So this part would be a minus 2, and it would have canceled with this plus 2 over here, which would mean that we wouldn't have this 1 over h part. So that's why this failed. If you want to get down into the weeds there. All right, well, exam 1 is coming up, so we'll have a little bit of a break while you prepare for that. And as we get into our second big unit, we're really focusing on the derivative, but we will mercifully have different techniques for finding it, which will make it a lot easier than taking limits.